Hello everyone. Today we're going to solve questions on equilibrium constant as I promised last time. This lesson would work for both IB and A-level chemistry students. Let me just check that it's live. Yes, it is live. Okay. Right. So I have started marking A-levels just now for this year, so I don't have much time, and I promise today's lesson will be short, like I think 30 minutes max. So what we'll do is we'll just solve a few questions. I took them from A-level from Save My Exams, yeah, but these are like A-level style questions. But in IB we would have similar ones. So um, you would like both IB and A-level students can solve that. Right, so let's start. Let's just start. And first question, it's this one. I'll read it out and then we'll solve it. So a chemist carries out an investigation on the equilibrium system shown below. So we have an equation, obviously reversible. And the chemist mixes 0.46 moles of CO, 45.45 moles of NO. The mixture is left to reach equilibrium at constant temperature. The student analyzes the equilibrium mixture and finds that 0.25 moles of NO remains. The total volume is 1 dm cubed. Write the Kc expression. What are the units? Well, yeah, we'll start with this, just basics, and then we'll do some calculations. So remember what's Kc? Kc, it's equilibrium constant, right? That shows how far equilibrium lies to the right or to the left. So it's written as concentration of products to the power of coefficients over reactants. So for this equation, we write it as Kc, and then in the numerator we have nitrogen to the power of 1 because the coefficient is 1 times, yeah, not plus, times CO2 to the power of 2 divided by the reactants, CO squared times again NO to the power of 2. So be careful with the brackets. The square brackets are essential because they denote the concentration. If you put round brackets, it's used for Kp. If you're doing A-levels, you know what I'm talking about. For IB, you don't need Kp, luckily. So, but you always have to use square brackets for both A-level and IB. So that's concentration at equilibrium of these species. Then what are the units? So the easiest way to find the units is to just calculate the powers of the Kc at the top and at the bottom. So at the top in the numerator we have the power of 1 and the power of 2. So that's concentration cubed. Right, I will just denote it like this: concentration cubed divided by, and at the bottom you have time like squared times squared, so that's concentration to the power of 4. Right, so when you can work with units like you would with numbers. So something squared times, for example, 2, well, maybe 3 squared times 3 squared, it's 3 to the power of 4. So the powers are added up, and what we end up with is 1 divided by the concentration, right? Because you would cancel out 3 and 4, so you subtract 3 from both, so it becomes 1 over concentration, and 1 over concentration, it's 1 over mole per cubic decimeter. So concentration in these questions is always mole per cubic decimeter. And then to get rid of the fraction, this answer is not accepted. It has to be, you have to have like units to some power so that you don't have the fraction. So you have to lift those up, and when you do, the moles, they used to be to the power of 1. When you move them up, it becomes -1. So you change the sign of the power. And dm, it is to the -3, so when I move it up, it becomes dm3. So that's the unit, plus 3. That's the same question. Yeah, the same question, and I mean the same beginning. But then determine the value of Kc for the equilibrium mixture in part A. Show all your working. Right, so in the type of questions where you're given initial moles or initial concentration, so something that is, well, when you have concentrations or moles at the beginning of the reaction, then in this case you need the ice table. Usually it's very well, I mean, you see it's 4 marks, so probably for 4 marks, yes, you would have to calculate Kc with the Lon method. Sometimes if you see that you have, for example, have 2 marks or 1 mark, they might occasionally give you equilibrium concentrations right away in the question, then you just plug them into the Kc. Here these moles are not at equilibrium, these are initial ones because the chemist mixes them together. And for this type of questions, we need to use the ICE table. I stands for I is initial, C is change, E is equilibrium moles. Yeah, so let's do that. So I would write down initial moles, change in moles, equilibrium moles, and equilibrium concentration. This is something that a lot of people forget. Well, you will not forget, hopefully. So in the KC, remember, we're plugging in the concentrations. So you cannot plug in the moles. Sometimes you would get the same answer with moles and concentration, sometimes not, so don't take your chances. And we need to write that for every substance in our reaction. Yeah, so we need to write it for CO, NO, CO2, N2, and I'll just make it a table. Yeah, so see, that's like I stable initial, change, equilibrium. And let's just fill it in. So for what do we know from the text? We know that we had 0.46 moles of CO, so it's initial, and 0.45 moles of NO. CO2 and O2 initially they are not mentioned, but it is possible that you even have some products in the beginning of reactants. Sometimes they give these weird questions when they mix everything. Yeah, so all the reactants and all the products, not here. If nothing is mentioned about the products in the initial mixture, then you assume that they are zeros. So 0, 0. Right, what else do we know? Let's read on. So, okay, so they mixed that, and then the student analyzes the equilibrium mixture and finds that 0.25 moles of NO remains. So, after these reactants have reacted, they formed some products, right? No, yeah, they formed some products, and we know how much NO remains, because remember, at equilibrium mixture, you would always have reactants and products. It would look like reactants cannot fully react, but that's wrong, because you know that both reactions are happening forward and backward, but they're just happening at the same rate. That's why we see that concentrations are not changing. Yeah, that's the whole idea of the equilibrium. And they would tell you in these questions the moles of some substance at equilibrium. So in this case, they gave us the moles of NO that remains at equilibrium. So it goes here, not here, here. Yeah, NO and the mole, so 0.25. That's how much is left at equilibrium. And then from the substance for which we know the initial and equilibrium concentration, we can find the change, right? So that's usually that's how your table would look like after you have written down all the moles or concentrations that they give you in the questions. So initial you would probably know, and something for equilibrium, and then your next step would be to find the change. So if initially you had 0.45 moles of NO, and after the reaction, so at equilibrium, you have 0.25 left, which means that the change was minus 0.20. So reactants are used up, that's why it's with the minus. Yeah, and 0.45 minus 0.20 gives you 0.25. That's how much is left at equilibrium. And for the change line, we can apply the ratio. Yeah, so if we used 0.2 moles of NO, 0.2 moles of NO reacted, it means that the same amount of moles of CO reacted. So 2 to 2 or 1 to 1 ratio. CO is a reactant, so it is used up, so minus 0.20. CO2. CO2 is the product. Again, applying the ratio, it's 1 to 1 to anything, to CO or an O still 1 to 1, so it's plus 0.20. Yeah, it was formed. And for nitrogen, it's a 2 to 1 ratio, so plus 0.1. Okay, let me double check everything is working. Yes, so I lost it. Okay, there. Right, so let's see. So then let's calculate the equilibrium mole. So for CO, it would be 0.46 minus, well, okay, I can do that. My mental math. So 0.26 for CO2, so 0 plus 0.20. For N2, 0.10. Well, 0 plus 0.10. And then remember to divide by the volume, right? Because remember the formula that concentration, it's N over V. Oh, no, I wrote it in the worst possible place. C is still not there. Hold on. C, it's N over V. Now you can see it. Yeah, N over V. So we have the moles, and we divided by the volume. Well, in this case, it's 1 cubic decimeter, so that would not change the numbers. So 0.26 divided by 1, this everything is divided by 1. So that's what we found. So we found the equilibrium concentrations of every single substance. And that's it. And now we just plug it into the Kc. Kc expression we already know. I will just write it out one more time, but you have it from the previous question. So Kc, it's nitrogen times CO2 squared over CO squared times NO squared. And let's plug everything in. So nitrogen is 0.1. Did I do it? Yeah, that's right. 0.1 times CO2, 0.20 squared over CO 0.26 squared times NO 25 squared, yeah, and then we just calculate times 0.2 squared over 0.26 squared and 0.25. 0.95. I will leave it to two significant figures, right? Because everything else was to two significant, so I keep my answer to the lowest number of significant figures here. So the calculator value is 0.9467, so 0.95. Well, and the units we did it in the previous question. Okay, that was the question. Next, continuation. Yeah, so C. What does your value of Kc suggest about the position of equilibrium in this experiment? So RKC, it was 0.95, so it's less than 1. What does it mean? Remember, Kc is calculated as concentration of products over reactants. So if Kc is smaller than 1, so products over reactants, what does it mean? It means that you don't have, the numerator is small, right? So you don't have a lot of product. Here it's approximately 1, so but still it's less than 1. Yes, if it's less than 1, it means that numerator is smaller than the denominator, and it means that equilibrium lies to the left. Yeah, so forward reaction is not really favored. If Kc is large, then it means that you have a lot of products, so the numerator is large, denominator is small, and not many reactants. It would mean that equilibrium lies to the right. Okay, so we say that, and that's how we explain it, it's just one mark. Yeah? So we say that Kc is less than 1, which means that equilibrium is towards the left. Yeah, lies towards the left. And next question, same, but D. The chemist increases both the temperature and the pressure for the equilibrium mixture. The mixture is left to reach equilibrium again. What is the effect, if any, on the value of Kc? Explain your answer. Well, we're not going to talk about Le Chatelier principle. That's AS level, and in IB it's SL. Yeah, what we're doing now, it's HL. But remember that Kc is only affected by temperature, right? So equilibrium, yes, it would shift if you change the temperature and if you change the pressure, but Kc, just memorize it, okay? Kc is only affected by temperature, nothing else. Because if you change something else, the concentrations would just would readjust to keep Kc constant. Yeah, but temperature will change the value. So, okay. And now let's see. So we know that pressure does not affect. Yeah, I will write that. I don't know why it's 1 mark though, because I think it should be an extra mark for pressure. I'm not sure, but this is from Save My Exams. Hopefully real examiners would be the people who do real exams, they're more generous. But I would say, just in case, that pressure does not affect Kc. Kc, and then let's now look at the temperature. So how do we think, how like what's the deal with the temperature? So think about where equilibrium would shift when you change the temperature. Okay, so the temperature has increased, right? A reaction is exothermic. Negative delta H, it's exothermic. So if you increase the temperature, you know that equilibrium would shift to the endothermic side, so to the left. Yeah, Le Chatelier principle. And then what does that mean? It means that you have less products. And remember, Kc is products over reactants. So if you have less products, what would happen to Kc? It decreases, yeah? But remember, so this logic can only be applied to temperature, nothing else. If you change concentration or pressure, yes, equilibrium would shift, but Kc would not. But for temperature, that's the easiest way to go about the Kc. Okay, so pressure doesn't affect. What effect, if any? Okay, and temperature, we say when temperature increases, equilibrium, shifts to the left. And here, guys, a lot depends on your board. For example, for AQA, you have to say because it opposes the change. For all other boards, just say to the left, but because the forward reaction is exothermic or backward is endo. So the wording might slightly differ based on the board that you're doing. But the idea is the same. So when temperature increases, the equilibrium shifts to the left because the forward reaction is exothermic. Is exothermic, and that means that Kc decreases. That's enough of an explanation for any board, well, except for maybe equilibrium shift could be explained better in terms of Le Chatelier principle. But if you say that equilibrium shifts to the left, that means automatically for examiners that you understand that Kc decreases. You could say that numerator becomes smaller, that's fine as well. Right, what's the time? 10:20. Okay, we still have time for a few more questions. And I don't want to go back to marking, so yes, let's do a few more questions. So next one, dinitrogen tetroxide and nitrogen dioxide coexists. Okay, so we have equilibrium. A chemist adds 4 moles of NO2 to a container with the volume of 2 cubic. You see, not 1 anymore, so if you miss the volume here, you lose a mark. Well, 1, but still, we like all marks. The container is sealed, heated to a constant temperature, allowed to reach equilibrium. The equilibrium mixture contains 3.2 moles of NO2. Calculate the value of Kc. First question that you have to ask yourself is, do you need the ice table? Yes, because they give you initial moles. As long as they give you initial moles of something, you need the ice table. So, well, let's do that. So I would write down, we don't need that, initial, change, equilibrium, and concentration, yeah, ICE. And substances, we have NO2 and N2O4. Okay, what do we know? Now we go through the text. So we have 4 moles of NO2, that's initial moles. N2O4 is not mentioned, so we assume it's 0. What else do we know? The volume, I will highlight it so that I don't forget about it later. Then the container is heated. Okay, at equilibrium, mixture contains 3.2 moles of NO2. So this goes here, moles at equilibrium for NO2. And now I find the change. So I know initial moles, I know equilibrium moles. So what's the change? Minus 0.8. Yeah. Now for the change line, I can apply the ratio. So if I have 2 NO2, I get 1 mole of N2O4. So the ratio is 2 to 1, which means that the change for N2O4 would be plus 0.4. Why plus? Because it's the product, right? So you form a product. And 0.4 because it's 0.8 over 2. And so at equilibrium would have 0.4. And then the concentration. So I just do, again, moles over volume. So 3.2 divided by 2 is 1. Well, yeah, I should have done it. 1.6, and this one would be 0.20. Yes, and then we plug it into Kc. Kc, which we don't have. Yeah, you see it's 5 marks. So 5 marks, let's see. We go products of reactants. So guys, I can see you. Oh yeah, I can see the questions. I'll answer a bit later. Hold on, let's finish that one and then I'll answer your question. So it's N2O4 divided by NO2 squared, right? Squared because there is the 2. And then we plug in the concentration. So 0.20 divided by 1.60 squared. 1.6 squared is 0.078. Again, I'll put it to 2 significant figures. No, actually, here I have to put it to 3. Yeah, because it's 333. So, well, 781 then. And, right, and let's now talk about the units again. So the units, they didn't ask, but let's just do it. So the units for Kc. So we have concentration to the power of 1 divided by the concentration squared, which means that I get 1 over concentration. So 1 over mole per cubic decimeter, so that becomes moving up, right? Please don't leave it like that. It's such a pain when I have to, like, a lot of people just leave the fraction. Do not leave the fraction, because we're not allowed to to give you a mark, even though I can see that it's correct. So minus 1 dm3. Right, now question, um, how to be good in organic chemistry? Well, that's a good question. If I knew the answer, I would be very happy. Well, I think for organic chemistry, the most important part is to make sure that you know all the reactions. And in my experience, all those flow charts, maybe if you're using flow charts, they just do not work. So I think the best way to study and learn all the reactions is to just separate them by class. Yeah, for example, study all reactions of alkanes first. Yeah, so just write it down from your textbook. Then also the preparation of alkanes. How can you prepare alkanes? Then the same for alkenes. All the reactions that alkenes can undergo, and then how can you make alkenes from other classes. I did start a series of live streams similar what you're asking. Yeah, so I did alkanes, halogenoalkanes. I guess you can find them on my channel, but then I stopped. I don't know if you have if you feel like that would be helpful, we can continue. But of course it's not all of the organic, right? You also have to know the mechanisms, and the mechanisms, well, just write them down 50 times, and then if let's see if that would help. I think it helps everyone. So if a student writes a mechanism 50 times on paper, the same mechanism, then everyone memorizes it. Of course, it requires some time, but it will pay off later on. All right. One more question, and then I let you go. Well, it's a similar one actually, but with a slightly different, more difficult ratio. So let's do that one. So, okay, so again, we have the reaction. Let's see if I can do it in 5 minutes, because let's try. So, okay, so we have a reaction, and then the chemist mixes together 10.40 moles of nitrogen, 22.5 hydrogen, and pressurizes the gas's volume. Again, let's highlight it so that we don't forget about it later. The mixture is allowed to reach equilibrium at constant temperature and without changing the total volume. The mixture contains 5.60 moles of NH3. Calculate Kc, including units at this temperature. To three significant figures, I also highlight just because I know I will forget. 3 significant figures. Again, ask yourself, do we need the table? Yes, we do, because they gave us the initial moles. Yeah. Okay. Actually, I on purpose chose the questions where we need the ice table just to practice the ice table, but we will also practice other questions when we solve like full past papers together. Okay, the table. So initial, change, equilibrium, moles, equilibrium, concentration, nitrogen, hydrogen, NH3, and okay, now let's fill it in from the text. Yeah, based on the text. So what do we know? We know that chemist mixes together 10.40 moles of N2, 22.50 hydrogen. Again, NH3 is not mentioned except for moles at equilibrium, right? But it wasn't mentioned in the initial mixture, so we assume it's 0. And then we know that the equilibrium mixture contains 5.60, so that goes here. Yeah, 5.60 moles of NH3. From the column where you know both initial and equilibrium moles, we find the change, so it's plus 5.60. Then we apply ratio to the change line. All right, let's see. So nitrogen is in 1:2 ratio, so it means that for 5.60 you need twice less, yeah, nitrogen. So it's 5.60 divided by 2, which is 2.8, with the minus because it is used up, right? It's a reactant, so reactants are used up. And then hydrogen, you can apply either 2:3 ratio with NH3 or 1:3 ratio with nitrogen. You'd get the same number, obviously. So I will apply ratio to nitrogen, so it would be 2.8 times 3, 8.4. And what's the sign? Well, the sign would be negative because again it's a reactant, so it is used up. And then and then what's the moles at equilibrium? So 10.4 minus 2.8, which is 7.60, and then 22.5 minus 8.4, 14.1. And then the concentration, so just divide the moles by 5. Remember, concentration is moles over volume. So 7.60 divided by 5 is 1.52. And then 14.10 divided by 5 is 2.82. 5.60 divided by 5, 1.12. That's our concentrations. Now let's write down the Kc expression and plug all the numbers in. So Kc, I'll write it here. Product over reactants to the power of coefficients. So NH3 squared, yeah, that's the product. And divided by N2 to the power of 1 times H2 to the power of 3. And then plugging in. So 1.12 squared over nitrogen 152, hydrogen 282 cubed. And now I have to not mess up the calculation, times over 1.52 over 2.82 cubed. That is 0.0368. I will keep my answer to 3 significant figures because I have 4 significant, but then 3 and 3, right? So I keep it to the lowest number of significant figures, so to 3. And now the units. Okay, let's think about the units. So Kc, what do we have? We have concentration squared at the top and concentration to the power of 4 at the bottom. Now you cancel out, so 2 minus 4, yeah, or 4 minus 2, so it's 1 over concentration squared, yeah, so like you cancel these powers out, and that is 1 divided by mole per cubic decimeter squared. Then I will open up the bracket, so it's 1. When it's like this, so you basically multiply the power, so it's mole to the power of 1 times 2, so that becomes mole squared dm3 minus, well, negative 3 times 2 is negative 6. And then you move those up, so it becomes mole negative 2 dm6. Yeah, so you move up by changing the sign of the power. All right, that was my last question for you and for myself. So next time, I don't remember which topic I planned for next time. I think it was pH and buffer solutions, but if you have any requests for specific topics that I should cover, please let me know. I'm very responsive, and we can adjust our lessons yet based on the most requested topics. You can leave your comments if you have any questions, and I'll see you next time.